Now, the situational awareness article says that there are three main drivers of progress in AI recently. Compute, just having more and larger computers working on it. Algorithms, being smarter. And what they call unhobbling, which is trying to get it to do new things. So we'll talk about these in turn and try and evaluate both what the contribution of these things are to the recent past progress and whether there's room for them to drive future progress. So first of all, let's talk about compute. This is basically the number of calculations that go into training and running a model. And this has been increasing very fast. We're going to talk about flops, which are floating point operations. GPT-2, back in 2019, the training of that is estimated to have taken about 4 by 10 to the 21 flops. By the time you're at GPT-3 in 2020, it's gone up by about 2 orders of magnitude, so it's about 3 by 10 to the 23 flops. This is both running for longer and running with a lot more graphics processing units. So about a 2 orders of magnitude improvement over a year or two. By the time we're at GPT-4, we're up to about 10 to the 20, few by 10 to the 25 flops, another 1.5 to 2 orders of magnitude improvement. Now, this improvement is not due to Moore's law. Moore's law, remember, tells you that computers are getting faster, that every couple of years you get twice as many microprocessors on a chip. But that's positively glacial, very slow compared to this. That only gives you 1 or 2 orders of magnitude a decade, whereas here we're talking about 2 orders of magnitude, an order of magnitude or more a year. This is mostly due to people just spending more money. Back in 2019, spending $1 million on training a artificial intelligence large language model seemed like a lot of money. Nowadays, hundreds of billions are spent on training these models. People have bought vast numbers of graphics processing units, and certainly multiple billions of dollars are spent on training them. So that's got a lot stronger. Here, for example, is the training compute and floating point operations, flops, against year, and it seems to be about on average of 0.6 orders of magnitude a year. You can see the most famous models are using way more than the average, but overall that's what's going on. People are spending more money, running bigger data centers with more graphics processor units. Has this finished? Almost certainly not. The tens of billions people are currently spending to train models is not the end. People are building clusters of the hundreds of billions, or even people even thinking about trillion-dollar training clusters. Are there enough chips to allow this all? Well, most of the chips produced by the cutting-edge fabs like TSMCs are actually used in phones. So if more of those get diverted into graphics processing units, there's certainly capability to build a lot more of these big graphics processing units. So most people in the field think that another maybe 2 to 3 orders of magnitude by 2030 is entirely plausible. So this has certainly driven things up by maybe 3 to 4 orders of magnitude in the last 5 or so years, and there's room for more. So that's compute. How about algorithms? Lots of researchers trying to figure out smarter ways to train the AI, and this is also a big source of improvement. It's a bit hard to disentangle it, but you can look, for example, at how much it costs to run a model that achieves a particular thing. And what you find is that a model, here for example, is a model that achieves a 50% performance on a particular mathematics benchmark, and the cost for that has dropped by about 3 orders of magnitude over the last 2 or 3 years. So a model now that can do the same thing at maths as a model from 3 or 4 years ago does it at 100 to 1,000 times lower price. And the graphics processing units and electricity haven't really changed, so what that change is being driven by is just being smarter. It's not just brute force, run more GPUs, bigger data centers. It's being smarter, figuring out how to train more efficiently. People have attempted to measure this, and the basic idea is that the efficiency is doubling roughly 8 months. So you're getting a few orders of magnitude improvement, not from just throwing more computers at from brute force, but actually from being smarter. Now, this may be harder going forward. Maybe the obvious things have already been figured out, so now we're having to chase the less obvious algorithmic improvements. That's certainly plausible. But on the other hand, there are also a lot more companies doing AI research and a lot more AI researchers. So maybe, like in many other areas of science, the problem is getting harder, but there are more and more resources being thrown at it. So most people think there's probably another 1 to 2 orders of magnitude by 2028 that's possible. Possibly more, as we'll see later. One thing that could limit that is data. One big reason why the AI systems have become more powerful is because they've been trained on ever larger amounts of data. But the current big AI models have basically been trained on the entirety of the internet, on every YouTube video. So where do you go from that? Maybe you can scrape up a bit more internet information, but you're not going to get another order of magnitude worth of data to train it on. Every book that's ever been written has already been scanned and put in, and it's not enough. Where do you get more data from? There are progress in many sub-areas of AI which are bottlenecked by this. For example, self-driving cars. They put cameras on cars and drive them around, and every time they fail they see, okay, we have to train it better to deal with this, but there's just not enough driving footage to train them. A human can learn to drive with 100 hours, but it takes a lot more than that to train these things. What companies like Tesla currently do is they run their cars around using self-driving, and every time something goes wrong and the human has to take over, they say, okay, there was a situation, maybe a bin bag blew across the road in front, or there were road cones on one side, it was pouring with rain, and a pedestrian walks out, or it could be some weird situation that the AI can't handle. They will then simulate that 10,000, 100,000 times using a computer game simulator and feed that in to train it. So they're producing artificial data to help train it. Robotics is another situation. You can build robots and then see every time it falls over you learn something's wrong, but you can't build the millions of robots and get them falling over in millions of different ways that you'd need to train these large language models. These models require unbelievable amounts of data. So they're actually often simulating it. They're writing computer simulations of robots and using that to produce the artificial data to train it. Likewise, training artificial intelligence to do maths and physics problems, they've trained them on every textbook ever written and every problem on the internet, but that's not enough. So now they generate, using programs like Mathematica, to generate ever more problems to train the AI on. So could this limit things? We've hit data limits already, but there are possible ways forward using synthetic data, which might actually be better than the internet. The internet is getting bigger all the time, but a lot of it's now AI-generated slop, so that's actually not helping you. If you train on crap, you get crap out. So what the people are working on now is trying to get better curated data, which eliminates the crap to help things. We do know that humans learn much faster than AIs. If you look at the number of words a baby will learn up to the age when it becomes a fluent adult speaker, that's many orders of magnitude less than what an AI needs to be able to speak as well as an adult human. So clearly, unless you believe there's something mystical like a human soul, if you believe that a human brain is just a neural network, there are better algorithms that will allow learning much faster. So between synthetic data and better algorithms, maybe this is not a limitation, maybe it is. I'm not enough of an expert to tell. Most people in the field think it's not a limitation. The third source of benefit is so-called unhobbling. These are whole new approaches to AI. In the last few years, the first one has been reinforcement learning, which is what took GPT to ChatGPT and made it from something that was a novelty to something that was actually useful. A more recent breakthrough pioneered by companies like DeepSeek is chain of thought reasoning, which is where the AI doesn't just give you what immediately comes into its brain, but spends a bit of time thinking about things. AIs are now beginning to use tools. They can go away and use a maths tool, maybe go and search the internet, and they're getting bigger and bigger context lengths where you can feed a lot of information, get to bear it all in mind when coming up with something. So these are things that have happened in the last few years. Future models might, for example, have long-term memory, where they can remember what you asked in the past and use that to help things in the future. They can be personalized to you. They can learn a lot of things about you and use that to help aid you. They might be able to use computers and the internet much more than they can at present. They might consult with other AIs. Google produced a research tool supposed to come up with new research ideas where they basically have a whole bunch of different AIs that argue amongst each other. One might play the role of the curmudgeon-y person who says, no, that's not feasible. Another person might be the wild brainstormer, and they might bounce ideas backwards and forwards before coming up with a conclusion. Also, you might, for example, allow your AI to go away and think about something for a month and then come back. How much would it do in that time rather than just giving you an answer within seconds? So what all these things do, here's an attempt, again from the situational awareness paper, to look at how these different models, physical compute, algorithmic efficiencies and unhobbling, have changed things in the past and will change things in the future. So over the last 5 years or so, there's been roughly 3 to 4 orders of magnitude of improvement in compute, 1 to 2 in all algorithmic efficiency, and unhobbling maybe 2 orders of magnitude. So we're talking about 6 or 7 orders of magnitude. So that's why AI has done so well recently. We've had 6 or 7 orders of magnitude, a factor of 10 million improvement in what we can do. How about going forward? Well, long term it's hard, but if we look just at the short term, so the next 5 years or so, there's probably another 2 to 3 orders of magnitude of compute. Opinions differ, but people are certainly currently trying to raise funding to build compute processor units at that sort of level. Algorithmic efficiency, it's really hard to say, but there's no reason to believe it's going to stop. There's certainly nowhere near the limit of what the human brain can do, so there are probably some more algorithms that people can invent. Might give you, this is very uncertain, maybe 1 to 3 orders of magnitude improvement. Unhobbling, who knows? Probably something big there. That might actually be the biggest of all, but we don't really know. But the basic point is we've had overall maybe 6 or 7 orders of magnitude improvement in the last 5 years, and there's no reason to believe we won't get at least 4 or 5 orders of magnitude in the next 5 years. So AI is not going to stop. So if you count the orders of magnitude, we went from preschooler level, 2 orders of magnitude later we're at elementary school later, 3 orders of magnitude later we're at smart high schooler level, and maybe a couple of orders of magnitude after that we're now at undergraduate level. So if you go another 4 orders of magnitude, which we would be at by late 2027, what are we going to be? At the Nobel Prize winner level? Who knows? But it's certainly there's no reason to believe we stopped here. Some people think there's this decade or bust. This progress we've talked about in orders of magnitude will stop at some point. For example, compute. By the time it's costing you 10% of world GDP to build the next processing unit, that's probably going to stop. By the time every chip from the biggest fabs is going into graphics processing and training AIs. So progress won't stop, but progress might slow down just to follow Moore's law, which is much slower. But the many orders of magnitude a year sort of progress we've been seeing recently, most people think that it will go until about maybe 2030, but by then we'll be having trillion-dollar clusters. There's just not enough money in the world to build bigger ones, and maybe most of the smart algorithms will already have been invented, and the smart unhobblings. So maybe we're in the middle of the reason things are going so fast at the moment is because we've had so many orders of magnitude improvement in the recent past, and they'll probably continue for at least a few years. But if we don't get to superintelligence in 5 years, it could be a very long time. So it's this decade or bust.